Hey everyone, here is the third video of 5 for solving and graphing polynomial equations. And we're going to pick up with what we left off on video number 2. And that's when we have polynomials that we cannot factor, we use the possible rational roots along with some other theorems to help us solve and graph the polynomial function. So going back to the example from yesterday, let's look at how we can use the possible rational roots along with Descartes' rule of signs to solve the polynomial function below. Okay, so yesterday we had this cubic function x cubed plus 3x squared minus 10x minus 24. We were able to find the possible, remember that it's definitely just possible, not for sure, rational roots p over q, and these numbers all came from finding the values for p, which were the factors of our constant, and divided by the q, the factors of our leading coefficient of 1. So that's how we got all of these numbers. Okay, so for Descartes' rule of signs, the number of positive real roots of a polynomial of equation p of x, and that's a positive x, I know it seems silly to note now, but you'll see in a minute, but p of positive x equal to 0 with real number coefficients is equal to the number of sign changes between the coefficients of the terms in the equation p of x, or is less than this number by a multiple of 2. So, looking at x cubed plus 3x squared minus 10x minus 24, you see that we have a positive number first, then positive, then we had a negative 10, then a negative 24. So it makes it easier to write out the signs in this way. So you have a plus, so it's still the same sign, but then it changed to negative, and then it stayed negative. So there was only one sign change. That means that the number of positive real roots is 1. Okay, we can do a similar thing to find the number of negative roots. And this is the second part of Descartes' rule of signs. And the number of negative real roots of a polynomial equation p of x equal to 0 with real number coefficients is equal to the number of sign changes between the coefficients of the terms of p of negative x. So that's where it's a little bit different than the previous one. Or is less than this number by a multiple of 2 again. So we're still looking at the number of sign changes. But what we do is we take negative x and plug it in parentheses where there used to be a positive x, and then we want to simplify that to determine how many sign changes we had. So here we'll plug in negative x, and negative x cubed will still leave us with a negative in the front, x cubed. But then the negative x squared becomes a positive x squared because a negative squared is always positive, so that still remains positive. Negative 10 times the negative x is now a positive 10x, and then the negative 24 remains the same. So in this case, we had two sign changes. We went from negative to positive, it stayed positive, then went to negative again. So we had two sign changes. So that number of sign changes, that will inform us that the number of negative roots, real roots, is either 2 or 0. Because remember, it's either equal to the number of sign changes or less than the number of sign changes by a multiple of 2. So we had 2, that's where we get the 2 from, and then minus 2 would be 0. Okay, so we've determined that there is one positive real root, and there are either 2 or 0 negative real roots. Notice we are saying specifically real roots because remember, we can also have complex or imaginary solutions. So our polynomial here is cubic. That exponent, the highest exponent was 3. So we know we're supposed to have a total of 3 solutions. But that can include multiplicities and complex or imaginary solutions. And we can now make Descartes' chart based on Descartes' rule of signs. So you'll see this, we have a column for positive, a column for negative, and a column for this c/I is complex or imaginary. So we know we have one positive root. So if we have one positive root, we have two options for negative, either 2 or 0. So if we have one positive root and two negatives, well, we have to have a total of 3. It must add to 3 since we know there are 3 solutions. So if there's one positive plus two negative, well, that's already 3 solutions, so we know there wouldn't be any complex solutions in that scenario. Or we can also have one positive and 0 negative real solutions, which means there must be 2 complex or imaginary for a total of 3 solutions. So these are the possibilities, and we can figure out which one it is. So using synthetic division, the remainder theorem and the factor theorem, along with the fact that we know that we have one real positive root. Let's try our possible rational roots, that's all of the p over q values, to see if we can find the positive real root. So there's no guarantee that the positive real root is a rational root, which remember the rational roots, all of the possibilities are all p over q. So these are all the possible rational roots. Okay, let's go ahead and look at the example. Okay, so remember from our example that all of our possible rational real roots are all of our p over q values are these 1, 2, 3, 6, 8, 12, and 24. And we figured out those from our previous video. But let's also use these two theorems as well. So we have the remainder theorem and we've got the factor theorem. The remainder theorem states that if the polynomial function p of x is divided by x minus a, then the remainder is equal to that function when we plug in a. In other words, we saw this whenever we were looking at synthetic substitution. Whereas we have the factor theorem, which if for any polynomial p of x, x minus a is a factor of p of x if and only if p of a equals 0. And we saw this whenever we used synthetic division. So remember, these two things look a lot alike. It's just that the remainder theorem told us that if we had the synthetic substitution, if we plugged in a number, the remainder, or the number at the end, was our y value if we plugged in x. And then for the factor theorem, we were looking to see if there was a remainder of 0. And if it was a remainder of 0, that means that that number was a factor of our polynomial. Really similar, just slightly different wording. So let's look at some of these possibilities here. Remember, we are guaranteed a positive root because in our Descartes chart, no matter what, we had one positive root. So we'll start with the possible positive numbers. And we'll use the positive numbers from our list of possibilities up here, and we will start plugging those in. So if we have 1, and we use synthetic substitution, so then you bring down the first term, and then 1 times 1 is 1, and then 3 plus 1 is 4. Then repeat, 4 times 1 is 4, and 4 plus negative 10 is negative 6. And negative 6 times 1 is negative 6, plus negative 24 is negative 30. So what we're looking for is this last number right here, if that number is 0. And we'll keep doing this for each of our positive numbers until we get one that has a 0. So 1, we end up with negative 30, so that's not the positive real root. 2, we end up with negative 24. That's not our positive real root. But when we get to 3 and we plug in 3, we'll end up with that 0, the remainder of 0. So since we got a remainder of 0, 3 is the positive real root. That's great news because knowing that 3 is a root, we can factor that out and write it as this. Now if you're wondering, where did I get all of this information from? Well, since 3 is a positive real root, that means that x minus 3 is a factor. And then this second part, where did I get that from? Well, remember, we did use synthetic division here, so whatever was left over becomes part of the second factor. So this was a 1x squared, this was a positive 6x, and this was a positive 8. So the 3 being a positive real root, that is the x minus 3, opposite sign, and then the leftovers for the synthetic division is our factor. But this x squared plus 6x plus 8 factors into x plus 2 times x plus 4. So now we can clearly see all of our solutions, because if we take the x minus 3 and the x plus 2 and the x plus 4, set them equal to 0, since we're looking for when they are equal to 0, and solve for x, we'll end up with 3, -2, and -4. So now that we have solved the polynomial equation, we can now graph it like we did before. So the x-intercepts, remember that they are at 3, -2, and -4, and we found that by factoring. And then the y-intercept is at, go back to the original equation, so it's our constant term. So here that's at -24. And then the end behavior, we'll talk about that in just a second. So let's go ahead and graph this polynomial. And I'm going to start out by plotting these x-intercepts. So I have 1, 2, 3, -4. I've got -2, and 1, 2, 3. I'm going to plot my y-intercept of -24. That's way off the graph, so I'm just going to put a point down here just so I have something to connect it with. And then my leading coefficient of my polynomial is a 1, and it's positive. So my leading coefficient is positive, and my degree is odd since my highest exponent was 3. My leading coefficient is positive, so that tells me that my right arrow will go up. And since my degree is odd, odd means the left arrow will be the opposite of the right. So odd will go down over here. Now, we didn't have any multiplicities whenever it was factored, so we don't have to worry about it bouncing off the graph anywhere. So we'll just go through the points and connect them like that. It was a rough sketch. Finally, the end behavior of f of x. So we have f of x approaches -infinity as x approaches -infinity, and f of x approaches positive infinity as x approaches positive infinity as well. So for these last two examples here, I would like for you to just make Descartes' chart, and then we will go over those as a warm-up in class the next time I see you. So that's it, and I hope this all made sense. Please let me know if you have any specific questions, and I look forward to seeing you in class again. Bye.